Hello, Linear Algebra students, Math 2331. We are here to prepare for the final exam, and what I'm going to do is work the final from spring 2022. We get started with number 1, find all solutions to this linear system. All right, well, what we want to do is write down the augmented matrix for this system and perform elementary row operations. So we have 0, 1, 3, 2, 0, minus 1, minus 8, 2, 10, 2, 1, 2, and then we augment 6, 7, 18. The first thing, well, I want a leading 1, so I'm going to interchange row 1 and row 2. This will be my first row operation. So we interchange row 1 and row 2. Make sure you label the row operations. This is part of grading your work. Through the magic of my GoodNotes app, I have exchanged row 1 and row 2. Well, now you see I have my first leading 1, so I want to try to get zeros underneath. But I also notice if I look to row 2, I'm going to go ahead and divide by 2, sort of in the same step. So let's take minus 3, row 1, add this to row 3, and at the same time, we can take 1/2 times row 2. Row 1 has not changed. Row 2 becomes 0, 1, minus 4, 1, 3. And then row 3, well, I subtract 3 times row 1 from row 3. I get 0, minus 1. I have 10 minus 6, which is 4. And then I have 2 minus 3, which is minus 1. 18 minus 21 is minus 3. Okay. Really, I only have one more step to get myself to reduced row echelon form. So let's take row 2 and add this to row 3. This bottom row becomes a row of all zeros. Now you will notice we are in reduced row echelon form. We have leading 1, and then we have free variable, say t, and free variable r. Now we need to solve this linear system. So x3 is t, x4 is r, and then you notice x1 will be 7 minus 2t minus r, and x2, 3 plus 4t, and minus r. Okay, so my general solution, all solutions to this linear system, well, we have 4 variables, x1, x2, x3, x4. x1 is 7 minus 2t minus r. x2 is 3 plus 4t minus r. And then we have t and r. All right, here's all solutions to this linear system. We move on. Part B. Let A be the coefficient matrix of the above system. And we can certainly check. That's what we have written as our coefficient matrix. Answer the following. Well, there's not a lot of work we need to show here. First, we want to find a basis for the image of A. So you notice here, this is the reduced row echelon form of A. And we have leading 1. What that means is we can take the first 2 columns of the matrix A to have a basis for the image of A. Let's do this now. Take column 1 and column 2 of my matrix A. So this is 0, 1, 3, and 2, 0, minus 1. Next question. We want to find a basis for the orthogonal complement of the row space of A. That is what this is asking for. Well, we know the orthogonal complement for the row space of A is just the kernel of A. In other words, we want to find a basis for the kernel of A. Now, all we need to do, you see all the work is done here, is just imagine we have zeros here. And so this part, the 7 and the 3 would become 0. Maybe I can even copy this part and paste. So a general element in the kernel of A will look like this. And this is, well, it's T times something plus R times something, and those two elements will be a basis for the kernel of A. So it's T times, we see minus 2, 4, 1, 0, plus R times, we have minus 1, 0, 1. And then my answer I will do in blue. Here's my basis. We just take minus 2, 4, 1, 0, and this other vector that we see, minus 1, 0, 1. This completes number 1. Now we move on. Number 2, use elementary row operations to find the inverse of this matrix A. Well, what we need to do is augment with the identity. We have 1, 2, 2, minus 1, minus 3, and then 1, 2, 3. We augment with the 3 by 3 identity, and then we perform operations until we see the identity on the left-hand side, and then over here, and then we can just read off the inverse on the right-hand side. So let's get started. Let's get zeros underneath my first leading one. We have minus 2, row 1, add it to row 2. Minus 2, row 1, add it to row 3. We have to remember to do the row operations on both the left and the right-hand side of this augmented matrix. So minus 2, row 1, add it to row 2. We have 0, we have 1, we have 0. And then minus 2, row 1, add it to row 3. We have 0, negative 1, and 1. And then we have minus 2's here. Next step. Well, you see I have leading 1. So I can just make this negative 1 is 0, working down. So let's take row 2 and add this to row 3. Row 1, row 2 do not change. And here we get 0, 1, and then we have minus 4 and 1, like this. All right, we really only have 2 more steps. We want to make this a 0 and this a 0. Okay, so first, let us take minus row 3, add it to row 1. In this step, row 2 does not change, row 3 does not change. We have a 0 here, and then we have 5. We have negative 1, negative 1. And my very last step, we take row 2, add it to row 1. Row 2 and row 3 are finished. They do not change with this step. This becomes a 0. And then we have 5 minus 2, which is 3. We have a 0 here, and then we have this negative 1. And so we're finished. It says that A inverse, well, it's this matrix, which I will just copy and paste. This was number 2. Okay, T is the linear transformation from R2 to R3 such that T of 0, 3 is this vector, T of 1, 3 is this vector. We want to find the matrix associated to the transformation. This is a properties question. Now, we know the matrix. So matrix A, I will just remind everyone, this will be T of E1 and T of E2. We put these as columns in our matrix. So column, column. What I need to do is figure out what is T of E1, what is T of E2, and we can get these with properties. The first thing you'll notice is that, maybe I'll do this on the side over here. E1, which is 1, 0. This equals this vector. Well, it's 1, 3 minus 0, 3. Also, E2, which is this vector, 0, 1. This is 1/3 times 0, 3. Now, these linear combinations, which I can do just by inspection, this is what's going to help me figure out my matrix T. T of E1, this will be using linearity here. T of 1, 3 minus T of 0, 3. Now, we are given these two vectors. So this will be 5, 0, 1 minus this vector, which is 6, 1 minus 3. -1, -1, and 4. Okay, T of E2. This will be 1/3 times T of 0, 3. Because of the linear combination we talked about moments ago. So we get 1/3 times this vector. 6, 1 minus 3. 2, 1/3, -1. 2, 1/3, -1. Now, all I need to do is just put these as columns as a matrix, and we are finished. I will put a box around my final answer here. So T of E1, we put this as our first column. T of E2, this is our second column. This is the matrix of the transformation. This was a properties question. Okay, now I have this slightly rearranged, but here is my matrix A we just calculated. Next question. Well, we have part A and part B. We want to find the associated matrix of the following linear transformations. The first is geometric. We want to first reflect about the line 3y equals 4x, and then rotate counterclockwise by 3 pi over 2 radians. And then we are given the formula for reflection. Okay, let's see. We're going to calculate these two matrices separately, and then we will multiply. The order matters here. So first, we can write L, the line, as a span. Well, personally, I like to avoid fractions if I can. So let's let x be 3, and then y will be 4. And then you notice this certainly is satisfied. If x is 3, y is 4, well, we have 12 equals 12. This is on the line. Non-zero vector on the line. Very nice. Now the reflection will be 2 times the projection minus the 2 by 2 identity. That's what this is saying for us. The projection matrix, maybe I will put in gray so we see it. 1 over W1 squared plus W2 squared. We have W1 squared. We have W1, W2, W1, W2, and W2 squared. So in gray, without the 2 in front, that would be the matrix of projection. We take 2 times this matrix minus the identity, gives us the matrix of reflection. What do we have? Well, this denominator is 25. So maybe I'll do the off diagonals first because I'm just subtracting 0. You notice I have 12 times 2 over 25 for both the off diagonals. This is 24 over 25 and 24 over 25. For the diagonal entries, here we have 18 minus 25 over 25. This gives us -7 over 25. And then here we would have 32 minus 25 over 25, which is +7 over 25. We also discussed that the reflection matrix has the form AB, B minus A, such that a squared plus b squared is 1. And certainly, as a sanity check, this has that form. Okay, this is the reflection. Now maybe I will do a vertical line. What about the rotation? So this one, reflection. And then we have rotation. So rotation matrices is cosine, sine, minus sine, cosine. And 3 pi over 2, we draw a unit circle. 3 pi over 2 is here, where cosine is 0, sine is -1. So we have cosine, sine, minus sine, cosine. Now, order matters. So to get the matrix, our final answer, first we reflect, then we rotate. So it's going to go like this. First we do this, then we rotate. This is the correct order. Now we just have to multiply these two matrices, which is not too bad because one of them, well, has these zeros and ones. So we have 24 over 25, 7 over 25. Then the second row of the product will be -1 times the first row of this matrix. 7 over 25 and -24 over 25. This will be my final answer. Certainly, if you want to, you can pull the 1 over 25 out in front, but it's also fine like this. One more matrix of a transformation here, letter B. We want the orthogonal projection onto this two-dimensional subspace of R4. This will be a 4x4 matrix. Now, we are told we have an orthogonal basis. That's very nice. But what we know, we need to have an orthonormal basis for V, put those as columns of a matrix Q, and then we calculate QQ transpose. So let's calculate the lengths of these vectors. Well, you can kind of see they have the same length. So the length, if I call this, say, V1 and V2, the length of V1 and the length of V2 is the same thing. We have a square root. Well, each one has 3, 5, 1, and 1. So this will be 25 plus 9 plus 1 plus 1. You notice this is the square root of 36. So this is 6. Very nice. Now, my matrix Q will be 1 over 6. And then we can just put these two vectors as columns. 3, 5, 1, 1. And -1, -1, 3, 5. Well, this is not a matrix of projection. In fact, this isn't even the right size. This is 4 by 2. We're looking for a 4 by 4 matrix here. And as I mentioned, what we want is Q, Q transpose. So we can recopy matrix Q and then write down Q transpose. The first column becomes the first row, 3, 5, 1, 1. The second column becomes the second row, -1, -1, 3, 5. So I'm going to leave this 1 over 36 all out in front because it makes my life a lot easier. Now we know from theory this matrix is symmetric, and you can either multiply the whole matrix out and then make sure it's symmetric, or if you're careful with your dot products, you can fill it out using symmetry along the way. Maybe I'll do it that way. Okay, so let's first fill out the first row. Here we have 9 plus 1, which is 10. We have 15 plus 1, which is 16. We have, well, you see this is 3 minus 3, which is 0. And then we have 3 minus 5, which is -2. Okay, this matrix must be symmetric. And so I can go ahead and fill out this column. Saves me a little bit of work. Next row. Well, we've already figured out the 2, 1 entry. So we can start here. We have 25 plus 1, which is 26. We have 5 minus 3, which is 2. Then we have 5 minus 5, which is 0. Once again, I know this is a symmetric matrix from theory, and I feel I was careful in filling out the second row. So let's fill out the second column. Must be like this. Next row. Well, we've calculated the 0 and the 2, so we can start here. We have 1 plus 9, which is 10. And then we have 1 plus 15, which is 16. Okay, once again, must be a symmetric matrix. That means this must be 16. So we just have one more entry, which is 25 plus 1, 26. Well, we know the length of the projection of a vector is always less than or equal to the length of the vector. Okay, if you consider this 1 over 36 in your matrix, this would be projection of E1, projection of E2, projection of E3, projection of E4, which means all the columns must have length no more than 1. In particular, what that says for your matrix is that certainly if you count this 1 over 36, everything you see in absolute value should be, well, less than or equal to 1. If I had a 44 here or anywhere with this 1 over 36 in front, I would know I made a mistake. So it's kind of a sanity check when you're multiplying these two matrices. Number 5 is true-false. We have 10 true-false for 10 total points on this particular final exam. I will remark, I have a whole other true-false video that gives you more practice if you're preparing for true-false questions. But for now, let's go through these 10. First question, the set here, x, y, and R2, such that 2x plus y equals 1 is a subspace of R2. False. The reason this is false, well, 0 is not in the set. 2 times 0 plus 0 is not equal to 1. Next one, x, y, z, and R3, such that this is 0, and for x equals z is a subspace of R3. This one is true. In fact, we could write this as a kernel. This y is the kernel of, well, you see this would be 4x minus z equals 0. So we can write this as a kernel of a matrix, which would justify that we, in fact, have a subspace. Would be 5 minus 1, 0. And then 4, 0, minus 1. Wonderful. This next one, this set is a basis for R3. Well, we kind of have to look at the vectors and see if they look to be linearly independent. 3 linearly independent vectors in R3 will be a basis. And there's some zeros here. So you notice, the answer is going to be false. Because if I label V1, V2, and V3, then just looking where we have zeros, we can take 4v1 plus 2v2, and this will be equal to v3. Just check. 4 times this will certainly in the last coordinate we would have the 20, and 2 times this in the first coordinate we would have the 30, and now this middle one we would have 4 minus 2, which is 2. So vectors are not linearly independent. They are not a basis for R3. Letter D, we have 4 linearly independent vectors, V1 through V4. The question is V1, V2, and V4 linearly independent? This is true. You could justify this a number of ways with rank, for example, but we can just say no redundant vectors. If a larger collection has no redundant vectors, then certainly a smaller collection of that will also. E, W is a 3-dimensional subspace of R7, then the dimension of the orthogonal complement of W is 4. This is true because, well, the dimension of W plus the dimension of its orthogonal complement must be, well, the dimension that they're sitting inside. And so here, if this is 3, this would certainly have to be 4 to give us 7. Letter F, there exists a 3 by 2 that says 3 rows and 2 columns, matrix A of rank 2, such that A times 1, 1 is 0. Definitely not. This is false. The reason, you see, we have 2 columns. The rank of A equals the number of columns. And so the nullity, which is the dimension of the kernel, is 0. So certainly you can't have a non-zero vector in the kernel of the matrix. G, B is n by n matrix. B cubed is the identity. Then the columns of B are linearly independent. This is true. Well, we know the columns of B will be linearly independent provided B is, say, invertible, and there's a number of ways you can justify it. One is with a determinant. You could also just write it this way. We see B times B squared would be the identity. And B is n by n. And so in particular, that says B is invertible. And B squared equals B inverse. You could also justify with, as I mentioned, a determinant. There's no way the determinant of B can be 0 because the determinant of B cubed would be 1. There exists a 4 by 8. So we have 4 rows and 8 columns. Whose column span are 4? Sure, this is true. Take any 4 by 8 matrix of rank 4. Any 4 by 8 matrix with rank 4 will work. We have 2 more. If A is an orthogonal matrix, then X equals A transpose B is a solution to AX equals B. True. This is true. The reason, if you have an orthogonal n by n matrix, well, we know that A transpose equals A inverse for orthogonal matrices. So that will say, without a doubt, this is true. And finally, if we have an orthogonal transformation, T from R2 to R2, then T of 1, 0 and T of 1, 1 are perpendicular vectors. This one is false. Why? Well, we know T of 1, 0 dotted with T of 1, 1 will be, well, it's 1, 0. T preserves dot products, so dotted with 1, 1. And this is 1, which is not equal to 0. These were the 10 true false on this final exam. Number 6, QR factorization. We have matrix A. It has 3 columns. We want to find an orthonormal basis for the image of A and then write down the QR decomposition of matrix A. Okay, how does this go? Well, the very first vector, we take V1 divided by its length. So the length of V1, we have 1 plus 4 plus 4, all underneath our square root. This is the square root of 9, which is 3. Everybody, please, please, please get the first vector right. All we have to do is take the first vector, divide by its length. Okay, so my U1, we have 1 over 3, 2 over 3, 0, and 2 over 3. Then let me put some brackets around this. Next one, well, first we calculate the direction. So this next direction, we take V2 minus U1 dotted with V2 times vector U1. Now, I'll just recopy U1 here. Then V2 2503. And then we have a dot product. Okay, so we take this vector and dot with this one. What do we get? We have 2 plus 10 plus 6 all over 3. Let's write that. We have 2 plus 10 plus 6 all over 3. What is this number? You notice this is 18 over 3, which is 6. So I'm highlighting the numbers that will appear in matrix R in my QR factorization. So I will typically multiply this constant times this vector, then, well, subtract, because it helps me with algebra mistakes. So my first vector is 2503. And then when I multiply through by 6, I have 2, 4, 0, 4. Now we can subtract. We have 0, 1, 0, minus 1. It's not a bad idea right now, before we even calculate lengths, to take this and take this. We should have perpendicular vectors. In fact, we do. Very nice. Okay, so the length of this next direction, we can see square root 2. And I will highlight this also because it will go in my matrix R. Okay, now U2, we take the component of V2, which was perpendicular to the line spanned by U1, divide by its length. We have 0, 1 over the square root of 2, 0, minus 1 over the square root of 2. Now, third direction. This is the one where it's perhaps the easiest to make errors because we have more things to add in dot product. We take V3 minus U1 dot V3 times vector U1, and then minus U2 dot V3 times vector U2. So first, V3 is 0, 3, 5, negative 3. Subtract off, I will have a dot product times U1, and then I will have another dot product times U2. Okay, now we take this vector, dotted with this vector. Well, we get something over 3, and it will be 6 minus 6. Oh, this is 0. Now, highlight. This will go in my matrix R right here. And then we take this vector and dot it with this. It's going to be something over the square root of 2. We get 3 plus 3 over the square root of 2. So this number, it's 6 over the square root of 2. Maybe I'll write it like that at first, which is just 3 times the square root of 2. This will also go in my matrix R. Now let's simplify before we add these 3 vectors. So V3, I'll just recopy. Well, this one's very nice. This is the 0 vector. And then I subtract off, multiply through by 3 times square root 2. I get 0, 3, 0, minus 3. I just get the vector 0, 0, 5, 0, 0, 0, 5, 0. Well, very nice. We can see just by looking at it, this vector has length 5. We will highlight this number to put it in matrix R, and then we can see U3 is just E3. The standard vector, 0, 0, 1, 0. Once again, it's not a bad idea to check. This vector, or once you divide by the length, should be perpendicular to both of the ones above, and you can see that's certainly the case. So maybe I will just underline my orthonormal basis for the image of A. It consists of U1, it consists of U2, and it consists of U3. Wonderful. Now we have everything. I have everything I need for Q and for R. We can just write it down. So my Q, this is the matrix that just has U1, U2, and U3. Orthonormal columns. We can just recopy, or maybe I'll just copy and paste. Here's the first column of Q. Here's the second column of Q. And then the third column of Q. 0, 0, 1, 0. Matrix R, everything highlighted will go into this matrix. So first we put along the diagonal these 3 links, which are over here. 3, square root 2, and 5. We have an upper, R is always upper triangular, so we can put zeros below the diagonal, and then we can see all of the numbers. We want U1.V2, this is here, U1.V3, and then U2.V3, which is 3 square root 2. Now, if you don't want to keep track of all the entries along the way, we also know that R is Q transpose times matrix A, but I personally find it easier to just keep track of all the numbers as I'm doing Gram-Schmidt. So here is the QR factorization of A. Number 7, we want to use least squares and fit a line C0 plus C1t to these 3 data points, 2, 3, -1, -8, and -2, -3. The thing to remember as we get started here is the first coordinate is the t, and then the second coordinate is the function value, f of t. So, well, we're going to need this to set up the right linear system. Okay, so let's evaluate at t equals 2. We have C0 plus 2C1, and this should be equal to 3. Evaluate at t equals -1. C0 minus C1, this should be equal to -8. Finally, evaluate at t equals -2. We have C0 minus 2C1, and this should be -3. Immediately, we can write down our matrix A, and we can write down our vector B. We have 1, 1, 1. We have 2 -1, -2. Vector B is 3, -8, -3. Now, AX equals B is inconsistent. In fact, we can see it here. You zoom way in. Here's these 3 data points. And you notice they do not fit on a line, and so AX equals B is inconsistent. We will need least squares here. Well, how do we solve least squares? Let's write down the normal equation. We calculate A transpose A. We calculate A transpose B. To get A transpose, say the first column of A will become the first row, and then the second column of A will become the second row. So maybe I will just copy and paste A transpose for when we calculate A transpose B. Okay, great. Well, A transpose A should be a 2 by 2 matrix. A transpose B will be a vector in R2, and we get 3. We get 2 minus 2 minus 1, so -1. And then for the 2, 2 entry here, this matrix is always symmetric. Now, A transpose B, for the first entry, well, we get -8. And then here we have 6 plus 8 plus 6, 20. Here is our normal equation. A transpose A times C0 C1 equals A transpose B. This is always consistent. And in this case, A transpose A is invertible. We will have a unique least square solution. Maybe I'll calculate the solution that way. We have a 2 by 2 matrix, and so we can use our shortcut formula for the inverse. A transpose A inverse. We take 1 over the determinant. Here we have 27 minus 1, which is 26. Then we flip the diagonal and take negative of the off diagonal. So this would be 9, 3, 1, 1. This is the inverse. So my least squares solution, x star, it will be this matrix times A transpose B. Not the only way you can do it. You could also just solve this linear system by augmenting and performing elementary row operations. But what do I get here? Minus 72 plus 20, which is minus 52 over 26. This is negative 2. And then I have minus 8 plus 60, which is 52 over 26, which is positive 2. Okay, are we finished? No. Final answer is a function. So let's write our final answer. F of t, it's minus 2 plus 2t. This is our least squares solution. Now we move on. This matrix, 3 by 3, we are given the characteristic polynomial. First part, find all eigenvalues with their algebraic multiplicity. Well, we're given the characteristic polynomial, which is a very nice thing. So we can write them down. We have 3, and minus 1. If you want to write it explicitly, the algebraic multiplicity of 3 is 2, and the algebraic multiplicity of minus 1 is 1. Next part, for which values of y is the matrix diagonalizable? Well, it all comes down to this one. If we have geometric multiplicity of eigenvalue 3 equal to 2, diagonalizable. But if the geometric multiplicity of eigenvalue 3 is only equal to 1, then we don't have enough linearly independent eigenvectors, and the matrix will not be diagonalizable. So let's figure this out. Let's take A minus 3i. We have minus 2, y, 2. We have 0, 0, 0. And then we have 2, 5, minus 2. We need this matrix to have rank 1 so that the nullity is 2. And that would be geometric multiplicity of eigenvalue 3. Well, you see we can just take one row operation here, really, to figure out the rank. Let's take row 1 and add it to row 3. What do we get? Well, we have minus 2, y2. We have 0, 0, 0. And then we would have 0. We have y plus 5 and 0. What I need is this matrix to have rank 1, as I mentioned, or equivalently nullity 2. So A minus 3i has nullity 2 if and only if y plus 5 equals 0. This says y equals negative 5 is our answer. And this would yield the geometric multiplicity of 3 being 2. And that would say we have diagonalizable matrix. Y equals negative 5 is the answer here. I like this question. Number 9. Here we're going to calculate the determinant of a 4 by 4 matrix, and then on the same page answer some other questions involving determinants. Now, we know we can find determinants using row operations and cofactors, and quite often, at least personally me, I will bring in some row operations to introduce more zeros into my matrix, then jump in with cofactors. So if I stare at this matrix, you see this first row and the last row, they differ only in one spot. So by doing just one row operation, I can bring in a lot of zeros to this matrix. So let's do this now. The determinant of A, well, let's take minus row 1, add it to row 4. And if you add a multiple of one row to another, it does not change the determinant. So row 1 stays the same. Row 2 stays the same. Row 3 stays the same. And then I have 0, 1, 0, 0. Oh, this is very beautiful because now I just expand about this row. Cofactors. Well, what's the sign here? Plus, minus, plus, minus, plus. We have a plus 1. Now, if you like doing minus 1 to the I plus j to remember the sign, this is minus 1 to the row 4, column 2. So you see this will be positive 1. Okay, then we cross off and cross off. We're going to have this 3 by 3 matrix. 3, 0, 1, 5, 1, 4, 1, 2, 8. Well, I'll just expand about the first row because at least I have 1 0 here. So this will be positive 3 times a 2 by 2 determinant. And then this would be plus minus plus. So it'll be plus 1 times another 2 by 2 determinant. Here we cross off, cross off. We have 1, 4, 2, 8. And then cross off, cross off. 5, 1, 1, 2. Well, what do we look at here? You see, we get 8 minus 8, which is 0. So really, I just have this one determinant to worry about. So the determinant of A will be 10 minus 1, which is 9. A has determinant 9. Next question, is A invertible? Why or why not? Well, yes, it is. Because the determinant of A is not equal to 0. Next question. Okay, now we have M and A. Oh, A is the matrix above, so we know the determinant of A is 9. Maybe let's write this. Very nice. Now M is some other 4 by 4 matrix with determinant 1/3. We want to calculate the following determinant. Being 4 by 4 is an important part here. All right, well, let's calculate. We have 4 rows, so factor the minus 2 out of every single row. We have minus 2 to the 4th. Then we will have determinant of M times determinant of M times, well, the determinant of A transpose is always the same as determinant of A. And then the determinant of M inverse, 1 over determinant of M. Now, you see this one and this one multiply to 1. So altogether, what do we get? Minus 2 to the 4th is 16. And then the determinant of M is 1/3. And then the determinant of A is 9. Altogether, you see we get 16 times 3, which is 48. This was a properties question. Here's a 3 by 3 matrix A. We are told lambda equals 5 is an eigenvalue for A. We want to find a basis for this eigenspace. How do we do this? Well, we want A minus 5i. We subtract 5 from the diagonal. We have 1, 4 minus 1. We have 1, 4 minus 1. And we have 1, 4 minus 1. Oh, we can see the reduced row echelon form here is just the first row and then 2 rows of zeros because, well, this is a rank 1 matrix. we could take -1 at row 1, add it to row 2, -1 row 1, add it to row 3, like this. Okay, so we have some t and r. x2 is t, x3 is r, x1. This will be -4t plus r. So a general element, maybe I'll write this here, in this E sub 5 looks like this, -4t plus r, t, r. We can write this as t times something plus r times something. And these two vectors will be my basis for this eigenspace. We have -4, 1, 0, and then 1, 0, 1. Okay, let's write our basis down. We can just recopy these two vectors. Next question. Okay, we need to write down matrix A before I scroll down because we have some other questions. So let's recopy matrix A. We are asked two questions. Is a certain vector an eigenvector for A? So let's recopy matrix A. We have 6, 1, 1. We have 4, 9, 4. And -1, -1, 4. The first one we ask is this V, -1, 1, 0, an eigenvector for A? If so, find its corresponding eigenvalue. All we need to do to figure out if this is yes or no is just multiply. We need AV to be a multiple of V if the answer is yes. It's -1 times the first column plus 1 times the second. So I get -2, I get 8, and I get 3. Oh, this is a no. Next question. Is W, which is 1, 1, 1, an eigenvector? If so, we find its corresponding eigenvalue. We proceed just as we did in letter B. We take matrix A times vector 1, 1, 1 and see if this is a multiple of 1, 1, 1. So here I have 10 minus 1, which is 9, 10 minus 1, which is 9, and then 4 plus 4 plus 1, which is 9. This one is going to be yes, because we have this is 9 times 1, 1, 1. So AW is a multiple of W. The answer here is yes, with lambda equals 9. Now we're going to have to use everything we've done so far. Letter D, diagonalize A, which means we need to find an invertible S and a diagonal matrix B such that A is SBS inverse. Okay, well, we know matrix S consists of our eigenbasis as columns, matrix B as the eigenvalues along the diagonal, but the order must be the same, so in the correct order. What were our eigenvalues? We had 5, 5, and 9, which means this one better be the third column because that was the eigenvector corresponding to the eigenvalue 9. And then these two, -4, 1, 0, and I could put in any order. So -4, 1, 0, 1, 0, 1. These were two linearly independent eigenvectors corresponding to lambda equals 5. Those you could put in either order as long as they are in the first two columns based on my matrix B. Okay, so here is S, or 1S, that works, and similarly 1B, that will work. Last question, number 11. We have singular value decomposition, which this will be fun. Now, we are given a 3x2 matrix A, and we are told what A transpose A is. Certainly you can check if you want. We want to find the eigenvalues of A transpose A. I'm going to use the shortcut about characteristic polynomial, and so I'm going to need its determinant. Maybe I will calculate this on the side. We have 100 minus 64, which is 36. Okay, what is the characteristic polynomial of A transpose A? We have lambda squared minus the trace times lambda plus the determinant. And this factors. We have lambda minus two things, two numbers that multiply to 36 and add to negative 20. This will be, let's see, negative 18 and negative 2. You can check this works. So the roots of this polynomial are the eigenvalues of A transpose A. We have 18 and 2. Next part, we want an orthonormal eigenbasis for A transpose A. Well, we have two eigenvalues. So let's calculate for each one. For lambda equals 2, we subtract 2 from the diagonal of A transpose A. We have 8 minus 8 minus 8 and 8. This is one where we can just see the reduced row echelon form by looking at it. It is going to be 1 minus 1, 0, 0. So initially, maybe I will call this, say, x1. Just find some eigenvector for this eigenvalue. We could take the vector 1, 1, say. It's not unit, not yet, but perfectly fine. Let's do lambda equals 18. We subtract 18 from the diagonal of A transpose A. We get minus 8, minus 8, minus 8, minus 8. Once again, we can just see the reduced row echelon form. 1, 1, 0, 0. And just to get some non-zero vector in this eigenspace, we could take, say, negative 1, 1. Perfectly fine. Now, these are not unit, but if you notice, they have the same length. So length of x1 equals the length of x2 square root of 2. So to get the orthonormal eigenbasis, we just take each vector, divide by its length. We will have two vectors. Right here. Here's our orthonormal eigenbasis for A transpose A. Fantastic. Let me make this slightly smaller. And we move on to the next part of this question. List the singular values of A. Well, these are square roots of the eigenvalues of A transpose A, but listed in a descending order. So sigma 1 will be the square root of 18, which we can write as 3 square root of 2. And sigma 2, this is the square root of 2. Letter D. We've been working towards this through letters A through C, but we want to calculate and clearly label all three matrices, U, sigma, and V. Let's think about sizes and talk a little bit about the theory before we jump into this. So we want A to be U, sigma, V transpose. U and sigma are both orthogonal matrices, which means in particular they're square. Also, it's the case that sigma has the same size as matrix A. So here A is 3 by 2. Sigma will be 3 by 2. This means V is going to be 2 by 2. It's the small one in this case, and U will be 3 by 3. Now, we have all of the work. We just need to fill in the values of sigma and V. Okay, we've done that above. Once we have that, the question is, how do we find U? Well, V is orthogonal, meaning V transpose is V inverse. So we will use, let's multiply by V on both sides. We will have a V equals U sigma. This will allow us to find this matrix. So we will take A times V1, will give us the right direction, but it won't yet be unit. A times V2 gives us the right direction, won't yet be unit. And then we'll have to fill in the third column of U to make it an orthogonal matrix. So let's get started on this right now. Okay, the sigma, same size as A. So we are looking for a 3x2 matrix. And the singular values go along the diagonal, but in descending order. Here, here, and then we put here, 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 and here. Next one, matrix V. This is the small one. Now make sure you get your order right. Matrix V has these columns, but we have to look back. So corresponding to lambda equals 18 is this one. That's going to go in the first column because that's where we put that singular value. So the first column is going to be here, minus 1 over square root 2, 1 over square root 2. And then this one was an eigenvector corresponding to lambda equals 2. And here's the singular value. This will go in the second column. So we can copy and paste. Now, AV is U sigma. As I was mentioning, we need to calculate AV1, which will give us the right direction, but won't yet be unit. Matrix A is this matrix. We have 3, 0, 1, minus 3, 0, 1. And then multiply by, this is V1. Well, you see we get minus 6 over square root 2, minus 6 over the square root of 2, 0, 0. What does that tell us? Let's start writing out my matrix U. This gives us the right direction, not yet unit. Well, you can see, we divide by the length, we get minus 1, 0, 0. Okay, now let's calculate AV2. When I multiply A times vector V2, I get 0, 0, 0, 0, and then I have 2 over the square root of 2. So this is the right direction, but it's not unit. So you can see the second column of U will be 0, 0, 1. Now what do we do next? We need to fill out the third column really in any way you'd like, such that we keep U to be an orthogonal matrix, meaning this third column better be unit and it better be perpendicular to the two that came before. So let's just do this. Here's my matrix U. So we have everything. We have sigma, we have V, and we have U. Now, if you have time, you could certainly multiply, take V transpose, and multiply U, sigma V transpose. You will get back matrix A. But this is the end of this last question. And this is the end of this final exam. I hope this video was helpful for you. Thank you so much, students.